Great. Fine. So today, what we are going to do is we are going to, say a lot about Verma modules and stuff. So we are going to start off with some, some primary things that we want to say about it, and then we will go on to a little more details as we go on with the class. Okay, so that's the plan. So so remember, when we are looking at mode expansions, you have this particular mode expansion where this is the usual sort of LoRa expansion that we did. And when we define this sort of state operator, state operators sort of correspondence by this. Okay, so by saying that, if you have this field, if you have this sort of primary field, you can act it on the state on the vacuum state to get a primary state phi. Okay. Now, if you want this to be well defined, and that would mean that let's act on with the modes, and that means that phi nm has to be acting on the vacuum has to be 0 when n is greater than minus h and m is greater than minus h bar. So we can actually simplify and we can write phi as actually minus h and h bar acting on 0. Because if the things for the higher ones will have factors of z in here, and that when you take the limit of z going to 0, that will just drop off. And we have also encountered this. So what you're left up is with just one field. Just remember this. We are just going to do a little bit of notation first before we go on to something else. So let's consider for a moment the energy momentum. The stress tensor and the instates. So if you are looking at t of z, then it's as you know, z to the power n minus 2. The weight, essentially h will be equal to 2 and ln's. So this, if you act on the vacuum, just gives you this guy, right? So in that case, so this, t of z acting on 0 just is equivalent to the state that you have here. So this is the particular field, and this is the state. Okay. Similarly, if you do it from the del z, then you have n minus 3, and then the state that you will have, which is linked up with this guy, is L minus 3, and so on. So if you act more and more, dells on it, you will go to higher and higher L's out here as well. All right. Now you can also look at the state which corresponds to the product of these two of these stress tensors, and that you can do as the following. So if you remember what we did last time, so if you are looking at the TT operator, so this is in this normal order, and so what is this? So there are two T's, so there'll be, so there's going to be a 2 plus 2, there's a 4 here, and the expression is going to be z to the minus and minus 4 and TT in the modes. Now remember from last time around that if you have these modes, so what is that going to be? So you'll have to look at the weights, and you'll have to order them in the right way. Okay, so that would mean that when you are looking at the TT operator, this TTN, that will be a sum over two. Two of these objects. You can just sit down and actually do this, and this is simply you have one where there's an n minus k l n minus k l k, and there's another one where these are switched. Okay. Now, if you were to act this on the vacuum, since you have k minus, the k is greater than minus 2, so this term starts at L minus 1, right? L minus 1, and it goes higher. So we already know that L minus 1 acting on the vacuum is equal to 0, and Ln acting on the vacuum is equal to 0 for n greater than equal to 0. So the first term, when you acted on the vacuum, that is going to give you that's going to just give you 0. And similarly, the second term is only going to going to make sense when you have n minus k less than equal to minus 2. Now you take into account that n here can only be equal to n has to be equal to minus 4. So at the end of the day, what you're going to get is that if you are looking at this particular composite operator, the state that corresponds to this guy is L minus 2 acting on the vacuum. Similarly, you can do things for the higher ones. And, for example, if you did T of del T, that will be a L minus 3, L minus 2 acting on the vacuum. You can sit down and do the rest of the things, but I guess you get the hang of what I'm trying to say out here. So we arrive at the following, following statement. So for every state phi in the Verma module, which is given by some L's acting on the vacuum, we can find a field which is going to be in this, T or del T, or more T's and so on and so forth. This is going to have the property that this particular field and the state are in one. They are in one correspondence. Okay, so this is something that's an important thing. Another thing that I would want to sort of lay down out here for the moment is what we call a conformal family. Now, let us look at a general primary state phi. Well, it has dimension h. And so as we know, this gives rise to this state phi, which you can also denote by h, which is phi minus h acting on 0. This is something we just learned. We also know that this satisfies the following relation. So ln acting on phi has to be equal to 0. So ln acting on phi can be translated through this equation, and it becomes h of n plus 1 minus n. So my h's and n's look very similar. This guy is an h. This one is an n. So you have this equation here. So now what you can do is you can look at the modes of the energy moment tensor with n less than 0 acting on the state, and they have these following fields. So let's just focus on the thing that I have here. So for example, they have so phi of z is simply h, it's just h, and this has a level 0. Del phi, on the other hand, is L minus 1 acting on H. This has level 1. If you're looking at del squared phi, then these will be 2L minus 1s acting on this H. If you're looking at the operator T phi, then this is going to be L minus 2 acting on H. So these are the fields. These are the states, and yeah, you can obviously go higher and see what is happening, but you see that you can write down with this field H and with the T's and the del's, you can write down these fields out here. Okay, so that is something that so let's go back to what we were saying. So the lowest lying state that we have here, this guy H, is called the highest weight state. Okay, now we'll say more on that just in a little bit. What I want to sort of emphasize here is the fact that each primary state gives rise to an infinite set of descendants. These can be obtained by taking derivatives and normal order products with T. This whole set is actually something which is called a, conformal family. Okay, so remember this particular notation here. Uh, so we will see that this essentially, if you are in this particular family, then conformal transformations of fields of this particular family move you around here itself. So this is what is going to be also related. This is what is also going to be loosely the Verma module V C of H. Okay, C and H. So this is what we are going to see a little bit more as we go. Okay, hopefully this bit is clear, and I hope the fact that what we did last time, the reason of my harping about normal order products is clear from these guys. So you have to make sure that you order your operators in the right way. Okay, moving on then. So we are going to be looking at something very important in this lecture and also in the subsequent lectures, and that is the highest weight representations. I just gave you a glimpse of this in the previous slide, but let us remind ourselves. This is something that you all know, but let's do this. Okay, let's remind ourselves of the theory of angular momentum. So SU2, right? SU2 is what we want to do. So the representation theory, representation space is spanned by these eigenvectors M of one of the generators. You usually are used to sort of calling this JZ. I've just called it J naught. So there is an inner product which is assumed to exist, so that these generators are actually Hermitian. So all the generators are Hermitian. And you arrange the two others into raising and lowering operators like J plus minus. Okay. So J0 with J plus minus gives you plus minus J plus minus, and J plus with J minus gives you 2J naught. Okay. What do we do then? We assume that the eigenvalue of M is bounded from above. So we will have a state, this J, which the J0 value of J is again the label J. And you cannot raise this further. So this has the maximum J0 value. So what does J plus do? J plus is going to raise the J0 eigenvalue, and J minus is going to decrease the J0 eigenvalue, right? So if this state is the state which is sort of the thing that is at the highest level, so in that case, its J0 eigenvalue cannot increase. So J plus acting on this state is equal to 0. Okay. All the other states, all the other eigenstates can be obtained from this state small j by acting on it with lowering operators J minus. Okay. So if you look at M has to be got from J by acting J minus n times. Acting with one J minus is going to lower the eigenvalue by 1. And so if you want to change the eigenvalue J to an eigenvalue M, so J naught of M is actually M of M. So if you want to do that, so you have to add J minus M times. You can also use the fact that J plus on J equal to 0 and J minus on the bra J is equal to 0 to actually get at what the inner product of these states are. As we can see that if you are looking at these particular representations, if M becomes less than minus J, then the norm actually is going to flip a sign, and that becomes no. So these particular representations will have negative norm states, and negative norm states means that these representations will become non-unitary. Okay, very good. The exception occurs where J is an integer or a half integer. Then what happens is that there's a state which is J minus 1, which has a negative norm, which has a 0 norm. So just, just very clearly, if you look at this and if you just put in the fact that there is minus, I mean, you put in m is equal to this, you see that this particular thing just goes off to 0. So this means that the state j minus 1 then has a 0 norm. And since, the states lowered from this, so m minus 1, the norm of m minus 1 is related to the norm of m. What happens is all the subsequent things, all the states that are obtained from it by acting with j minus also become a 0 norm state, okay? We will say that these are singular vectors and they decouple from this first j plus 1 states. So you can think of it as the following. So if you look at an operator A, which is built out of these generators Ji, then if you look at the matrix element of this operator A between these two states M and M prime, so here M is a state with positive norm and M prime is a state with 0 norm. We will see that you can actually work this out in a simple way, and we will see that this particular thing necessarily always goes to 0. So what happens is that the representation space is then truncated to the first j plus 1 states, and so then what you have at the end of the day is a unitary finite dimensional representation of SU2. Okay. So that's what this is, and this sort of logic is also very similar to what we are going to be doing for our case. Okay. So we are going to proceed in a very similar manner for the for the Virasoro algebra. Look at the algebra. Okay, look at the algebra, and from here it's apparent that we do not have two generators that commute. So we will choose a single one in this case L0, which will be diagonal in the representation space. Okay. This representation space, as we have said before, is also called a Verma module. And let H be this highest weight state corresponding to a primary of weight small h. So we know from before L0 acting on H is H, and Ln acting on H is equal to 0 for n is greater than 0. So you see that these ln's sort of act as so these ln's will lower the weight of H, and so it's very similar to what we have done before. So it's a sort of sad misnomer that these are called highest weight representations, but okay anyway. So so ln's, ln's are these weights. So ln's will decrease the weight for n greater than 0. So in a sense, we are saying that the weights are actually bounded from below by H. Now you can change this. You can change and you can act L minus n's on H to produce new states. And the set of all these states will be called this Verma module and will be labeled by V, C of H. C is the central charge and H is the weight of the state that we are saying. Okay, for example, you can look at the lowest lying states. This is like what we did last time around. So for level 1, you have H. For level 0, you have H. For level 1, you have L minus 1 on H. For level 2, you have these two states. For level 3, you have 3 states. For level 4, you actually have 5 states. So you see that this is sort of the partitioning of the integers. So it gives you P of L equal to 1 is 1, P of L equal to 2 is 1, and so on. L equal to 0 actually. So L equal to 0 is the P has to be equal to 1, and so on and so forth. So you see, up till here things match, and from here things become more and more. There are more and more ways of partitioning a number like we saw last time around. Okay, so as we said before, roughly speaking, the Ver module is a set of states corresponding to the conformal family of a primary field with dimension h. Now, what are we going to do? On this module, we are going to define an inner product by the usual, Hermitian conjugation of L dagger is equal to L minus M. L dagger of M is equal to L of minus M. Remember, this is the same way that we used to, define Hermitian Hermitian conjugation earlier, and we showed you this earlier. So if you were to have two states in this particular module of L, this particular guy, well, L of minus K1 to L minus Km, and here it's L minus L1 to L minus Ln. So the inner product of these states is just clearly this guy here. So what is going to happen is that the signs of these will change, and since it's a dagger, the ordering will also change. So this is what you have. So what is a very clear-cut upshot of this? A clear-cut upshot of this is that if you have if the string of these L's are not equal, if these two strings are not equal, then what will happen is that you are going to be left over with either something which has an extra L minus something, or something which has an extra L plus something, and that will just act either this way or this way and just give you a zero, basically. Okay, so the point that one needs to note is two states at different levels have zero in a product. Okay. This also follows from the fact that eigensubspaces of a Hermitian operator. Remember what was happening. You remember this, right? So you remember this guy here. So if L is equal to 0, so if L is equal to 0, so L0 dagger is actually equal to L0, right? So this particular guy is Hermitian, right? So you would remember from your earlier math methods classes and so on, that the eigensubspaces of a Hermitian operator, here L0, with different eigenvalues are actually orthogonal. So this essentially means that your inner product between these two different states at two different levels will be equal to 0. And hermitaticity also forces H to be real. Okay. A similar analysis holds for the anti-holomorphic section leading to a Verma module V bar of C bar and H bar. And the Hilbert space is going to be a direct sum of V and V bar. So this is what your Hilbert space of the system is. And you need to sum over all these H's. Okay. So this is what I was saying in some manner last time around. So now what we want to do, so the point that I want to stress on is that depending on values of C and H, the Verma module can have states which have vanishing or even negative norm. And if you were to restrict to unitary theories, having states with negative norm is not a good thing, so they have to be removed. So let's see how one does this. Okay. Okay, so let me first stop and ask you guys: is there something that is it all fine so far? Any questions so far? Okay, does not seem to be, and our internet is holding up today. Okay. So now we want to get to something that I call singular vectors or reducible modules. And reducible modules. So as I write here, it may happen that the representation of the Virasoro algebra comprised of all the states is actually reducible. What does this mean? This means that there's a subspace that itself is a full-fledged representation of the algebra. So states of this, subspace, or if you wish, the submodule, transform into themselves under any sort of conformal transformation. What will happen is that such a submodule is going to be generated also by a highest weight state chi. Okay, so chi acting, so ln acting on chi will have to be equal to 0 for n greater than 0. But remember, this state is not the not the highest weight state that you started off with. So it's also a descendant of some particular highest weight state. Okay, so it has to be primary, but it also has to be a secondary state at the same time. We will see examples of this, but let's see what happens with this. Okay, so any state except for this H, that is annihilated by all the L nodes, LNs, is called a null state or a singular vector. Okay, such states are going to generate their own Verma module V of chi, which is included in the original Verma module V of ch. We will see that these singular vectors are actually orthogonal to the whole, to the whole Verma module. So what is the thing? So you have a state of the Verma module, right? So this is something, and there is this this state chi. So what you can do is you can just, so this is some sort of norm. You can also so you can just conjugate this. It has to be the same. So this will just flip over, and what you get is this guy, right? Now we know that any L's with L, these N's, the fact that you have something like this here means that this guy has to be equal to 0. So any state of the Verma module that you take and you you look at the inner product of that state with chi, that necessarily has to be equal to 0 all the time. This is also true when you're looking at chi itself. Okay, so as I said, this chi has to also be a secondary, right? So if you're looking at chi itself, so chi will also will also have to be equal to 0. So remember, so this and if the norm of these chi's are equal to 0, all the descendant states of chi will also be equal to 0. Now, just to say this in another way. So through the operator field correspondence, what we also have is that the null state is also associated with the null field chi. As I said before, this null field has to be primary because all the ln's acting on it have to be equal to 0, and also secondary because since it's a descendant of this primary field phi of h. Okay, so this sounds a little weird at first, but it's very easy to sit down and think about it a little bit, and you'll find that this is the case. Now, what we can do is, so there was this question about what the irreducible representations are, right? And how you can get to the irreducible representations, or of the algebra that we are interested in. So if a Verma module contains one or more of these singular vectors, then we can construct an irreducible representation of the algebra by quotienting out the null submodule out of this guy. Okay, what does this mean? This means we identify states that only differ from a state. If there are two states which differ by a state of 0 norm, we are going to identify these states. If we do that, these will give you the irreducible representation. In a sense, you're just throwing out this sort of zero norm states. Okay, so then these, I mean, irreducible representations will contain fewer states, and we will call this MCH instead of VCH as we have been doing. All right, so we will explicitly see examples of this as we move ahead, but let us try and pause and go on to something a little more straightforward at the moment. So we want to do what? We want to look at unitary irreducible representations of the algebra. So now let us try to focus on the unitarity aspect. So what is a unitary representation? A representation of this particular Virasoro algebra is going to be called unitary if it does not contain any negative norm states. So this would mean that there is going to be a restrictions on the values of the central charge and the weights h. Okay, so let's to see this, let's look at a simple bound. Okay, let's look at the norm of L minus n h. So so the norm of this means you have to calculate this guy. And you see that if you want to do this, what you always need to do is you need to pull the creation operators on the left so that it can act on the bra, or the annihilation operators on the right so that this can act on the ket. So once you do that, you flip the sign of this. So what you get is, as you know, Ln. So what am I doing here? What I'm doing is simply Ln L minus n is equal to L minus n Ln plus of Ln L minus n, right? And here I've used the fact that this guy is nothing but L minus n Ln plus twice n L naught plus the central central charge piece. Okay, plus C over 12, blah blah blah. Okay, so if you just do that, okay, very good. So this is what you get. This is what you get. So this guy, obviously, this acting on this gives you 0. So you're left with this, and L naught acting on H is going to give you H. So there's a first term which is 2NH, and there's a second term which is there's a central term. Okay. Let's take H equal to 1. So this so what do you see out here? What you see is if there's an n cube, right? So if you take larger and larger n, this is the term that is going to actually be crucial to understanding how your norm is going to behave. So if you take, if you even take higher values of h, you can go on increasing this n, and then so for any central charge which is less than 0, if you go to high enough n, you would be able to turn the sort of norm of this into something which has a minus sign, right? So the negative norm states will appear if the central charge is less than 0. So this is something that is going to happen all the time. So let's keep that in mind. And also let's keep in mind that if n is equal to 1, then this term is not there anymore, and you're only left with this term. So you also have to make sure that h less than 0 is also something that is going to lead to negative norm states. Okay. So these are the two very clear-cut things. As I said, if c less than 0, the above term becomes negative for sufficiently large n. All representations with a negative central charge are hence non-unitary. For n equal to 1, we also see that the norm becomes negative for h less than 0. So we find this very straightforward analysis leads to unitary bounds. C greater than 0 and h greater than 0. Okay, so this is a very straightforward way of doing it. Now let's try to understand this in a little more detail. Okay, so the next 10 minutes or so, we will try and do this. I was actually trying to import a picture. Let me see if I can do that. Just give me a second, please. Let's see if I can. Yeah, these guys are here. Unfortunately, I can't show you the picture. I don't know what is going on. All right, so 7 point something. Yeah, for some reason, the only picture that I'm interested in is something that I cannot show you guys. But okay, so let's just my e-copy of this book doesn't have this picture. Weirder things have happened in life, but okay, maybe next time I'll just show you the picture or something else. Let's see. Yeah, so what I was saying is that you have this particular where did this go? Is my screen being shared? Guys, are you there?
Yes, sir.
Is my screen still being shared?
Yes, sir. Yeah.
Yeah, I'm just trying to figure out where this went. Says my screen is paused, and yeah, okay, hopefully back to meeting should help. Nope. Okay, yeah, very good. So many desktops open that I was making, life was becoming a problem. All right, so let's just look at this, and maybe next time around I can show you guys the picture that I wanted to show you. So the necessary and sufficient condition for unitarity are found by, if you look at the gram matrices of these, inner products between these particular basis states. So let's do this. So I will be the basis states of a particular Verma module, and this gram matrix we are going to denote it by this guy. Okay, so Mij is this guy. Remember that Mij is going to be so these are what, so i's and j's are what, so i's and j's are the things that you just saw, right? So this is for example, these are these states here which I wrote down for you. So these i's and j's are all of these guys. Okay, so these are my basis states, and the gram matrix is the inner product of these guys. Okay, now remember that this Mij has to be block diagonal. Why is that so? So if we have something which is, so mk has to be the one which corresponds to the level k. This is because the inner product of states between different levels will actually vanish. This is something that we stressed upon just a few minutes back. So now let's look at some particular generic state A, which is given by some particular coefficients ai into these states I. So the norm of this is going to be given. So you can write the norm of this as a dagger m into a. So if m is Hermitian, it can be diagonalized by a unitary matrix. And then you can rewrite this in the following way. If B is U of A, then what you find is that the norm is going to be given by lambda I into Bi. So lambda I are the eigenvectors of this. Eigen values of this particular. Yeah, of M essentially. Now, what this is going to be, so there will be negative norm states if M has one or more negative eigenvalues, and there will also be singular vectors if one or more of the eigenvalues are going to be equal to 0. Okay. Yeah. Accordingly, the Verma module will be reducible. So let's see this in the actual sense, and let's see what this means. So for example, let's look at the particular states mk. So if you're looking at m naught, this is just h with h. This let's normalize this to be equal to 1. So M1 is going to be something that you are looking at the first level. So this is the norm of L minus 1. Okay. So there's just one state, right? So this gives you twice H. Good. Now, when you're looking at the next level, then you have more than one state. So what you want to do is actually you want to find out the matrix this. Okay. And so what is this particular matrix M2? So this matrix M2, you can just sit down and do this. So so this is all these states. So there's one state this, and there is another state this, and you want to find out the inner products of all of these guys, right? So there's this entry, there's this entry, this entry, and this entry. This one and this one, obviously need to be the same, but we'll see that in a bit. So let's do this one first. So this is L2 L minus 2. This is going to be nothing but 4L naught here, and there is going to be a C over 2 here. Just remember that L n with L minus n gives you twice n L naught plus n cube minus n C over 12. So if you have n equal to 2, this is 8 minus 2 C over 12. So this is the C over 2 that you see out here. Okay. Very good. Similarly, what you can find is you can find out this one as well. So you take these two guys, use the Virasoro algebra, and you get to 3L minus 1. And when the dust, when you actually take this through each other, then you get a 6L naught, and so you have a 6H here. You can similarly check that this other thing also gives you 6H, and it's a little bit more of a calculation to show you that this guy here gives you 4H plus 8h squared. So the entries here in M2 are going to be, so M2, I've not written this down. So let me write this down in another color. So this is what? This is 4h plus c over 2. This is 6h. This is 6h. And this one is 4h plus 8h squared. Okay. So this is our matrix M2. So this is just 4h plus c over 2, 6h, 6h, and 4h plus 8h squared. Now we want to make sure, we want to figure out what the eigenvalues of this guy are, and we want to make sure that the eigenvalues are actually, both the eigenvalues are greater than 0 if we have to have this and this to be unitary. All right, so let's see this. So what do? We look at. So, okay, let's just look at each of these things. So the first one is just 1. So 1 being greater than 0 is obviously trivially satisfied. So M1 gives you H has to be more than 0. This is already something that we have seen. And now the second thing is so M2 is going to give you something which is non-trivial. Okay. So the product of the two eigenvalues of M2 is equal to its determinant. So let's find out what that is. So if you look at what the determinant is, it turns out to be this guy here. And the roots of the determinant are given by, you can factor out an h from here, and then there'll be 2 more. So you can rewrite this determinant as 32 times h of h minus h11, h minus h12, h minus h21, where h11 is just 0, but h12 and h21 are these two guys. Okay. You can also find out what the sum of the eigenvalues is, and this gives you this. So now what we see is that the representation is not unitary whenever the determinant or the trace is less than 0. So we already know, that for every doublet CH which lies outside the first quadrant, this leads to a non-unitary representation. Now we see that there are also regions inside the first quadrant that lead to these non-unitary representations. I wish I could just show this thing to you. So in my attempt at trying to draw this, let me just try and do this. Okay, let me just do this real time. So this is going to be the first quadrant. We're going to draw h squared with c. Let me not get ahead of myself. So we are only going to be interested in the first quadrant. And let me also draw this line. Okay. So now let's get rid of this. There is a region like this. Horrible. But let me get rid of that. Say something like this. Okay, so this is 1, 2, and this guy is 2, 1, and this region in between is something that you do not want to get into. So this for example is, so this is c equal to 1, this is c equal to 1, this is c equal to 0. So what am I doing here? So at first, what have you seen is that if you were not to restrict things, so if you did not restrict things, this is the um, HC plane, then everything should would have been there, right? Now, if you were to use the first crude approximation, then all of these things will be ruled out. So this, everything which is in this particular region will be ruled out. And you'll only be left with the first quadrant. This essentially means that what you are doing is you are looking at c greater than 0 and h greater than 0. This was what we did with our first bound. Now with our next bound, so this is what we did in a very crude way to start things off with. So we did this, and that means you're sort of restricting yourself to this quadrant here. Okay. Now, even inside this, if you were to look at c, I mean, if this were the c equal to 1 line, so what we did with the M2 observation is that we saw that, I mean, this is something that I've not explicitly shown you, but there will be regions where these things are going to be, going to be negative, right? So you would have things here which are, I mean, if you were to look at just unitary theories, these regions will not be allowed. So as you go ahead, then you will see that there are even more things like this. So let me draw another line for you. So this is just for M2. For M3 you can do more. Maybe there's going to be another region which looks like that. Okay, this is going to be ruled out by the next level. So you'll have, I mean, another set which is being ruled out. Okay, so let me try and get this guy out from here. So this is 1 2, this is 2 1, and this is going to be something else. This is going to be 1 3 and 3 1, things like that. So as you go higher and higher, you're going to rule out more and more of this sort of parameter space that you have. Okay, so remember, this is only trying to rule out things between 0 and 1, but you're saying that with these unitarity bounds, you are being able to sort of rule out regions in the parameter space which is labeled by C and H. Okay, for those of you who are doing the thing with the bootstrap, uh, I hope to say a little bit about it at some point of time. But this is also very similar to the something. So you look at the parameter space of all these CFTs. Maybe you label them with the central charge and the weights, and there you put, I mean, constraints like unitarity, and you rule out the regions of the parameter space so that you can know where your CFTs, I mean, could lie. We will see that there's, I mean, we'll not see this in very great detail, but we will see it a little bit at least, that you would be able to actually for C less than 1, you have this great, I mean, well, I wouldn't say great, but it's a really nice thing happens. You have a discrete series of CFTs, and these things are going to be called the minimal models. I will try and see if I can give you a flavor for that last time around. But today I just wanted to end with this, that once you do these things, what you can do. This is something that I've not. So there exists actually. Okay, there exists a general formula due to KC is not CAC but COTS. So for the determinant of the gram matrix, and this is given by, let's just do this. Let's just write this down. So let's determinant of M hold the kth level is given by some alpha k product over Rs greater than 1 or times S less than equal to K H minus HRS, which is and this is P, this is K minus RS, where P K minus RS is going to be, so there is a form for, these guys. P is just the partitions of, P is just the partitions of the number, P is partitions of L minus RS. Okay, not L, sorry, K minus RS. K minus RS. So this is an integer, and AK is a positive number, positive constant. That is independent of H, R, and S. Okay, independent of H and C. I can also write down the form for you if you want to. It's not very illuminating, but let me do that nonetheless. So this is a K is product over, again, RS is greater than equal to 1, RS is less than equal to K to R whole to the S factorial into some M RS. I know this is very not very illuminating, but Katz actually wrote this down. I actually don't know, how to derive this. So if somebody can actually derive this for me, I would be happy to know that. Oh, this is not. So I'm just, so these are K's, okay. Okay. Very good. So I'll try and give you a few more formulae at the end of the day. So this is, in a sense, what is happening is you can figure out what the unitary bounds on a CFT are in this following way. Okay. So we will have a little bit more to say about it in the next class, but I wanted to just show you that this, sort of this idea actually is rather simple, and so it has a lot of very interesting, consequences at the end of the day. But the ideas, it's just the fact that you do not want to have any negative norm states in your theory, and you can do that by looking at the gram matrix, and that gives you a very good handle of things going forward. This highest weight representation would be very, very important for us, and we are going to be using it everywhere actually. So that's so this was actually an important lecture again. So next time around, I think Shudipto is going to be saying, is going to be giving us an idea about the Weil anomaly. But in the class after that, next Wednesday, that is, I will move on to, so I'll give you guys a more clear explanation of what these sort of null vectors are, because so far at least the discussion about null vectors may seem a little vague to you and you may not have understood it. And so I will try to make sure that I can show you how these null vectors are useful, and we shall do that with some certain examples. So I think I've already gone past 4 o'clock. I'll stop here, but before I do, any questions so far?
I have a general question.
Yeah, sure. Yeah.
So like I'm trying to think about like why there's this one-to-one correspondence between the states and the operator, like states in a CFT.
Mm-hmm.
So that is like related to the Virasor algebra, right? So like hypothetically,
Hello?
hear me? Hello?
Pratesh, you just went off for the last bit. I mean, I could hear just, hypothetically, and
Okay.
then after
So
that, it was not.
yeah. So like
Yeah.
hypothetically, like suppose if the Virasor algebra had some kind of abelian invariant subalgebra, then
Mm-hmm.
can we say that this one-to-one correspondence will still hold? Like,
See, what is happening in a sense is, think of it as the following. So if you are sort of thinking of it in the path integral sense, so think of the cylinder, for example, right? So you are looking at states. So you are thinking about states which are gotten by inserting. So you act with, so let's think about a free field theory, right? So what do you do? So what you do is you have a certain, you have a particular vacuum. You act it with some sort of some sort of an operator, say some creation operators, right? So from there you're going to generate another state. So what is being said is that so for every state that you have in a particular theory, you are going to act with a particular operator on the vacuum to get that state.
right.
So I don't think, having an abelian subalgebra in a symmetry algebra, I don't think is going to make anything very different in that way, I guess. It
Like
should not.
I was just wondering, like, because like we have done so far with just symmetry arguments, right? Like we
Yes,
just looked
yes,
at the algebra and
yes,
then,
yes, yes.
so like there should be some kind of argument for this one-to-one correspondence. So like that's what I was trying to think about.
In a sense, so okay. Again, I can take you sort of back to the so yeah, this is a little circular, since I'm saying that you can insert some particular operator, and then so as long as you're thinking of asymptotic in states, I think you're fine, in the sense that I don't have any counter example for you, unfortunately. So the state operator correspondence in a CFT is actually something that you get, and we've seen that, right? We've seen it that what are you going to distinguish a state with? So if you are going to distinguish two separate states, it has to be with this weights H, right?
Right.
So as we have seen that with the primary of weight H, that particular field, if you acted on on the vacuum, you generate a state. That particular state also has a weight H. Now you could think of adding some more, you could add some more symmetries onto the game as well. You could add some more charges into the game if you wish. again, that would lead to some sort of, some sort of operators here, and it'll also lead to some, some states. So the way that you're going to distinguish between these things will be the sort of eigen values of, of the states. And so these will be the, these will be, what the labels are of the states, right?
Right.
And
Yeah.
similarly, for the operators, you, there's another language to do that. It's sort of looking at, yeah, if you wish, so two sort of different ways of trying to look at the same thing. For example, in quantum mechanics, you have the Schrodinger way of trying to understand it, versus the Heisenberg way of trying to understand the same thing, right? So it's sort of similar in that sense. So you can understand the whole thing in the language of operators. You can also understand the same thing in the language of states, and there is a very clear map between the two.
Okay. So it's like it should be thought of as a outcome of this formalism. Like, is that? What
Yeah.
you're
So you can think of it. Yeah, you're free to choose. A way of trying to address it. So you can wholly address it in terms of operators, or you can also choose to think of it in terms of a Hilbert space and states and so on and so forth. So it's just two separate ways of trying to do it.
Okay.
As we said before, right? But if you are looking at at trying to look at it from the point of view of a Hilbert space and so on, then you need to separate out a particular time direction, and there are some associated things that you have to do with it.
Yes.
So
Right.
yeah. So any more?
Okay,
Yeah. So any more questions? Okay, there's something in the chat. Okay. Sean Jerry says you can see the screen. All right, if there are no more questions, then next Monday, Sudipto is going to speak about while anomaly, and the day after that, we will see null vectors in a little more details. All right, then, see you next week. Bye-bye.